Okay, example, forced oscillation. So let's pull up the problem. It's going to be this one. So damping is negligible for a 0.15 kilogram object. So that's telling us two things already that I want to write down. B, the damping is 0. M is 0.150 kilograms. For a 0.15 kilogram object hanging from a light 6.3 Newton per meter spring. Okay. So that's telling us the spring constant K. A sinusoidal force with an amplitude of 1.70 newtons. Let's see, drives the system. At what frequency will the force make the object oscillate with an amplitude of 0.440 meters? All right. So let's see. It is saying frequency, so we should probably talk about how omega is 2 pi times f. Omega naught for a situation like this, a mass on a spring, would be the square root of k over m. So we will want that at some point as a reference point. Alright, so we've got spring attached to wall, we've got mass somewhere in here. We have damping is equal to 0, so it's nice and simple, and then we have this attached to some kind of forcing function. So let's see. There's really no good way of getting at the answer except that we know it's going to follow some kind of x is a cosine of omega t, possibly plus a phase. And the amplitude is going to be a complicated thing itself. It's going to be f naught divided by the mass over the square root of, I believe it's omega squared minus omega naught squared, the whole thing squared. And then I believe we have a minus b omega over 2m or something like that. I'm feeling a terrible sense of regret right at the moment that I don't have that right in front of my face. Nope, it's just b omega over m. And it is squared. Alright, I'm not super feeling bad about forgetting that off the top of my head because it is A on the formula sheet. And B, we know the damping is 0, meaning this whole term is 0. Yay! Alright. So we do have a very specific goal for our amplitude. And I want to immediately rearrange this a bit. So I'll have the square root of omega squared minus omega naught squared, the whole thing squared. Still, for the moment, under the square root is equal to the forcing function divided by m times a. I'm basically doing a cross multiply thing here. Okay. Then let me see. Well, the thing that's going to cause trouble for us is that square root of something squared. Because we have no way of telling, is this part inside of the square root, actually I want that in a different color, is this stuff before it gets squared positive or is it negative? Is omega squared bigger than omega naught squared, or is omega naught squared bigger than omega squared? We can't tell which way it is once we've taken the square root. It introduces a sign ambiguity. So that's a problem, and hopefully you remember how that problem is resolved from your various math classes. The trick is, once we get rid of the square root and the squared, we split it into two possible solutions. One where omega squared is greater than omega naught squared, and the other one where omega naught squared is greater than omega squared. What does that do to the answer? Well, signs. So if omega squared is bigger than omega naught, we keep the sign as it is and let it go. And if we believe it's the other way around, we'll have our omega squared minus our omega naught squared, and we'll set that to a minus f naught over ma. Alright, I'm going to get the equations done for finding the omega. In both cases here. Okay, and then we'll take the square root, and at the same time let's think about frequency. So frequency is 2 pi, omega is 2 pi times the frequency, so we'll have this and that. And the last step to find any of these, f is 1 over 2 pi square root of omega naught is square root of k over m. So this is going to be square root of k over m squared, so k over m, plus f naught over ma. And on the other side, the other possible outcome, 1 over 2 pi square root of k over m minus f naught over ma. Alright, so let's see. I'm going to recopy some of the values here. Let's see, I've got 0.15 and 6.3. 0.150 kilogram, 6.30 newtons per meter. F naught, I believe that's like 1.7 or something. Yep. 1.70 newtons. I should remember it, I just looked at it. Yeah, we're targeting 0.440. A is 0.440 meters. Alright, so with those values, let's have at it. I'm going to find out what 1.7 divided by 0.15 times 0.44 is. I'm going to store that on my calculator because I'm going to want it. K over m, same deal, 6.3 divided by 0.15, and store that. Alright, so 1 divided by 2 times pi times the square root of my k over m plus my f over ma, and I get 1.31 hertz for this side, and on the other side, 1 divided by 2 times pi times the square root of my k over m minus my f over ma, and 0.641 hertz. Okay. You will see trickery like this with damped harmonic oscillations in your 1C class. If you're taking the electromagnetism at Pasadena, you are going to be seeing the same kind of trickery with these kinds of things under damped oscillation. Two possible frequencies that would lead to the same kind of amplitude. I know that I at least asked a similar question when I was teaching the 1C class. Alright, that is it for this example problem. We'll stop here and I'll see you. Actually, no, this was the last example problem for the chapter. So this should be the end of chapter 15 now. So next up, we'll be getting into some traveling wave stuff.